Hello everyone, welcome to this video. In this video, we are going to learn about SINDy using OpenMathAI. So, let's get started. What is SINDy? SINDy, or Sparse Identification of Nonlinear Dynamical Systems, is a machine learning algorithm used to discover the mathematical equations that govern the behavior of a dynamic system. Unlike traditional regression models, which mainly learn the relationship between inputs and outputs, SINDy identifies the actual differential equations that describe how the system changes over time. SINDy works by first calculating or receiving the derivatives of the system variables. It then creates a library of possible mathematical terms such as constants, linear terms, squared terms, cubic terms, and interaction terms. Using sparse regression, SINDy removes unnecessary terms and keeps only the most important terms required to describe the system. During prediction, SINDy uses the discovered differential equations along with the current system values to calculate how the variables change over time. Numerical integration methods are then used to estimate the future values of the system. Imagine we want to study the behavior of a nonlinear chaotic system. The system contains three state variables called x, y, and z. These variables continuously interact with one another, producing complex and rapidly changing behavior. SINDy can analyze the measured values and discover the governing equations responsible for this behavior. We will use a lower-end system dataset for the SINDy model. This dataset contains 500 data samples. The input features are x, y, and z, and the target outputs are dx dt, dy dt, and dz dt. The dataset also contains a time value for each observation. During training, SINDy learns the sparse nonlinear relationships between the state variables and their derivatives. It can identify equations such as dx dt based on x and y, dy dt based on x, y, and z, and dz dt based on x, y, and z. So, let's get started. Open OpenMathAI. In this demonstration, we use energy consumption by power prediction using SINDy model. Click Create New Project. Enter the project name as Power Prediction. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature, Signal Diagnostics. There is a free columns. First one is column its tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the SINDy model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration, Test Data Split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also the another feature is added that is trained from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of dz_dt, dx_dt, and dy_dt. Click Math and Code Preview. View the generated mathematical equation and source code. OpenMathAI provides expression of the data, detailed explanation of the expression, and an implementation code. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format: ANSI, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.